We're back with Math Man Mondays. It's a new year, so happy new year. We are now in 2020. Remember, hindsight is always 2020. It's not a new me, but it might be a new you. I don't know. But we are going to be doing some linear regression tonight so we can talk about those positives, negatives, and constants in your life. Really and truly, hope you guys had a great holiday. We've been off for a couple weeks from the stream as far as Math Man goes, just because I want to take a couple weeks off from teaching some math since I teach for a living and spend some time with the family and friends. So, truly hope you had a happy new year. Hope you had a good set of holidays no matter what you celebrate. And overall, just hope it was a good time. I know for me it was. In fact, my wife bought me some new markers, so we will be seeing some new colors this evening. And we're going to try these markers out. They seem pretty dope. But tonight we are talking linear regression. And we're going to talk about a couple different things. It's going to be more generalized to hopefully just give you kind of a lead in to review those type of problems in your class. You're able to do them without any crazy issues. So first and foremost with linear regression is we need to talk about what does it mean to have linear regression. And if I didn't throw my eraser on the board, on the floor, that'd be easier to get to. So when we talk about linear regression, I always like to give a project when I bring up linear regression. I give a general idea of what linear regression is about, and I always use NFL coaches and the amount of wins they had based off of how long they played. And that's a pretty good example because you kind of see that the longer the coach coached, the more games they hopefully won. Obviously, in some coaches' cases, that's not the truth, but in most cases, the longer you're around, the more games you win. So we actually have three types of linear regression that we need to think about. And when we talk about linear regression, we're really talking about just these XY plots. And the reason we bring these up is there's three types. And when we talk about linear regression, we're really talking about kind of scatter plots. Let me make these real quick. Sorry if that's really annoying on the mic. But you have scatter plots, and really what you end up looking for is you can look for a linear regression equation, which is very much similar to y equals mx plus b. There's actually two different ones depending if you're using a TI-84, 83, or any of the TIs. You can actually see y equals ax plus b or y equals b plus ax. They're both the same thing. You just need to watch where a is. So when you have a best fit line, you want to think about the fact that if you're moving upward left to right, we've talked about slope before. We're moving upward left to right and you have a best fit line. We're just going to imagine the best fit line is here. And what that means for us is that this is a positive correlation. And we'll kind of talk about what's called the correlation coefficient here in a few minutes, but that's a positive correlation. If you're moving downwards left to right, in other words, you have a negative slope, moving downhill, things are going not in a great direction for you, then that is a negative correlation. If you're just kind of horizontal line, you're just chilling, and you're going left to right and there's no change, this is what we call constant. Sorry. So you see these type of positive, negative, and constant correlations. If you look at sales numbers or anything that has to just deal with where you're comparing two different statistics, you could see this. So if we're talking about, for instance, years played and wins, it's up to you how you want to label them. We could have years here and then amount of wins here. What we don't see on any of these charts is I kind of keep this pretty consistent, but let's say we have one that's way over here. All right, if you have a point that's kind of way off on its own, this is what we call an outlier, and it negatively maybe that's not the right word. It affects your data, and what that means is it will actually pull your data in one direction. So in this case, it might make things seem a little bit more positive than they actually were. A great example of that is test averages. So if I was to give a test and most people score between 70 and 100, and then I have one person that scores 28, well, that one person becomes an outlier, and they're actually going to drag the average down because of how low they scored. So that's a good example of what an outlier is. If you're talking about a coach, let's say you had a coach that coached for 10 years and they only got 20 wins. Well, they would have been fired by then, but that kind of gives you an idea because most coaches are over 100 over that time as far as the NFL goes. In other sports, there's usually more games, so really hope they're over 100 at that point. But that gives you an idea of what positive, negative, and constant correlation is. We also have something that's called the how is it worded? The correlation coefficient, I believe. So the correlation coefficient is denoted by R. And the closer your R value is, if you have a positive correlation, the closer you are to 1, the stronger your correlation is. So if your correlation is 0.9, then you have a really strong correlation. But if you have a 0.5 correlation, then it's really moderate. And if it's anything below 0.5, you have a weak correlation. If you're moving in a negative direction, you want to think about that correlation coefficient being related to -1. So the closer it is to -1, the better. So you're looking for like negative 0.7 to 0.99. If it's negative 0.5 to negative 0.75, you're kind of in that moderate zone. Anything below negative 0.5 would be weak. And what that means, if you have a weak correlation, is maybe there's something wrong with your data that just doesn't work. Maybe you should evaluate it in a different way and reconsider the independent and dependent variables. What you want to remember is that you can pick a variable. For instance, if we're talking about an XY graph, we always pick X's and the output's a Y. So the Y value is dependent upon the X value that we picked. So that's kind of a way to kind of think about. You could change your independent, dependent variables, and maybe that helps you get better data, but also a better outcome. So some things to think about. Now, most of the time, like I said, you're going to be using a calculator. And there's actually some good sites you can actually use that will, when you plug in your data points, it will not only give you a graph, but it will output your equation, and it will output your correlation coefficient and everything for you, and it looks really nice. If I remember, I'll try to link one of those in the description of the YouTube video, so if you want to go check that out, you can. So the things you want to remember here is slope-intercept form. Jeez, I can't write today. Slope-intercept form is y equals mx plus b. When we're doing these correlation coefficients, so linear regression, we're using y equals ax plus b, or y equals b plus ax. When you're doing these data points, for instance, let's say we looked at the birth rate over the course of 5 years from 2014 to 2019, and we input that data, and then we have a last point. We say, hey, in 2020, how many kids do we think are going to be born? Your A value becomes that 2020, and you would input that. And it's kind of cool. So you leave that data out, you get your regression equation, you know where your y-intercept is, so then you plug in A, and bam, you're now given a birth rate. I have people that will do like, hey, are the Patriots going to go to the Super Bowl this year? Well, not this year because they got eliminated by the Tennessee Titans. But that just gives you an instance of, oh, hey, let's look at these different wins and loss rates, and like, let's see if we can predict how far they'll make it. So just a lot of interesting stuff that can happen with linear regression. It really gives you a great way to look at the positive and negative, see discrepancies. My favorite thing is I am very much hands-off when I give this project, where I have them pick a topic, pick their data, and then I have them explain, is their data weak, moderate, or strong? If it's weak, why is it weak? What could they have done to change it? Is there a better way they should have looked at it? Is the data just not useful at all? And then you can go and you can look at beyond that. It lets them kind of learn some of the definitions without me telling them, like, hey, what's an outlier? They find that out by themselves, like, hey, this one piece of data really messed everything else up. Well, what happens if you pull it out? And then we tell them, they pull it out and they look at it and they're like, oh, well, that really makes things look better. It makes my, coefficient actually closer to 1 or closer to -1, so now my data is strong. And those are the kind of things you need to look at. So you want to pay attention to outliers. Is there anything pulling you one way or the other? And really just pay attention to that. If you're using a TI 83 or 84, or really any of the TI series, there is an option when you're doing linear regression that you go to these tables, and you'll have tables and they'll be labeled L1, blah, 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 L2, blah, 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 L3, blah, 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 L4, blah, blah, blah. And you can go on and on and on and on, just like Journey. And really what the base set for this is, you would use L1 and you'd put your data, so data, input L2, data, and it would output, because the default setting is to use these two pieces or these two columns of information. So you're always going to be set to L1, L2. You can actually change that if you look at when you go to hit linear regression and ask you what information you want. There's a point where it says L1, L2. So if you wanted to read L3, L4, L3, L5, because you changed your dependent, or you changed something about your independent variables with the calculation, you want to see how they compare now, you can do that. Just be careful about that. You can clear these out. In fact, you can go up to the top, you can hit clear, and it will clear out, and then enter, and it will clear out the whole column. The thing you want to be careful about is if you hit clear, or if you hit delete on L2, L2 is gone. It'll delete the whole entire column, and then you'll have L1, L3, L4. And the only way to get that back is to factory reset your calculator. So that is not a fun time, and I do not suggest that. So without getting way too mathy today and doing a bunch of problems and showing you a bunch of stuff, I wanted to keep it really definition based. And then if you have some feedback or you have questions, you want to get more involved in it, I'd be happy to answer those questions and get more involved next week or in the future. Just feel free to always leave a comment or hit me up on Twitter, and I will definitely look into it, or I can actually do some problems over this. But I want to keep it kind of general, because I think actually getting involved and looking into it is much more interesting than me just throwing a bunch of problems out there and working through it. I think actually getting your hands a little dirty with and doing it is just different. So that is going to be it for tonight. Nice, short, and sweet. I really, like, again, I said, I hope you guys had a good new year. I hope your resolutions are working out so far. And truly hope it continues to go well. I know it's been going well for me. And happy Math Monday. I'm going to switch over to some games. I got to redo my setup real quick. And I'll probably be hopping over to Smite, because I have a tournament this coming up weekend that I want to be playing well for, because currently I'm not. And I will catch you guys next Monday with a new topic. Thanks for tuning in.